Yeah, so everyone should feel free to ask questions during the talk. I've never given a lecture before, so feel free to make comments and suggestions for improvement. Okay, so nominally I'm speaking about axions. Roughly speaking, the first lecture will be just introducing the problem that axions solve. The second will be actually discuss solutions to the strong CP problem, one of which is the axion, which is by far the most popular solution. And then on the third lecture, I'm going to talk about experimental techniques people are using to look for the axions. And there are a whole lot of them, and it seems to have become popular recently. All right, so the problem of the strong CP problem is essentially just what is the neutron EDM? So let's do this classically. Classically, this is a neutron. It has an up quark, a down quark, and a down quark in it. And the dipole is just sum of charge times distance, right? And so I drew it roughly like this. You can go say there's some angle here. This has charge 2/3, minus 1/3, minus 1/3. Do some vector algebra. This is 10 to the minus 13, I think it was, charge centimeters times some 1 minus cosine theta. So this is roughly speaking the size of a neutron. So this is sort of just what you would naively expect, just being told a neutron is made up of a up quark and two down quarks. And so what is the actual measurement, or like what is the value of the neutron EDM? So to do that, people actually use Larmor precession. So if you have an electric field that goes up and a parallel B field that goes up, and then you have a neutron in here, and let's say its spin is pointing in this direction, its spin will precess around the E and B fields with an amount, I don't know, let's call it a frequency that's proportional to basically the magnetic dipole moment plus the electric dipole moment, absolute value. Is this large enough for people to see? Okay. Okay, so then what they do is, okay, so point of note is that the spin of a neutron is parallel to its E and B, its dipole moments, because this is a vector and these two are also vectors, and so if there's only one breaking of Lorentz, like of direction, they have to all be pointing in the same direction or anti-parallel. Okay, so then what they do is they make a lot of neutrons that are all in some spin up position. Let's say this is spin up. And then they wait, like apply an E field and a B field. They wait something like 10 seconds. Then by then it'll rotate it to something like this. And then they measure how many have gone, are now in the up position, how many are in the down position. And this is determined by basically the frequency. And so they do this once with a parallel E and B field, both pointing in the same direction. Then they do it again where the E field and the B field are anti-parallel. Let's say this is the spin. And so then this has a frequency that's UB minus DE, because now these guys are anti-parallel. And so then they just measure both of these values very well and then take the difference. So this is one of the simplest ways of doing it. They have started to do more fancy stuff, and basically this is the essence of how you measure the neutron EDM. And they've measured it to be, let's see, D is less than 10 to the minus 35, I think it was. Sorry, 26. That's very off. 26 charge centimeters. So if you wanted to say it, this implies essentially that this angle theta here classically, it's less than 10 to the minus 13. Or in other words, the proper way to draw the neutron, classically, is d, u, d on a straight line. So this is the classical formulation of the strong CP problem, which is essentially that the neutron EDM classically has this very special value. And these looks like they're all flat on a line. At this level, classically, you can actually talk about two of the most popular solutions, sort of a little bit after the axion, which are there's two symmetries you can use to set the neutron EDM to 0. The first is parity. So under parity is literally just x goes to minus x, right? It's a mirror. If parity was a good symmetry of nature, it would set the neutron EDM to 0. So why is that? So if you take a neutron that has spin up, and let's say for some reason its dipole moment is also up. So how does the spin in the dipole transform under x goes to minus x? Well, as I wrote up there, the dipole is just charge times distance. So this means under parity, your dipole goes to minus dipole. Your spin vector, right, is more like equal to r cross p. And so under x goes to minus x, your momentum changes direction and your radius changes direction. So s goes to s. And so this means under parity, a neutron whose spin and dipole moment are parallel to each other transform into a neutron whose spin, well, let's say this is the dipole, and the spin is negative. And so there's only one neutron. We've measured this. And so these two things should be the same object, which means s is non-zero. So the only way for these two to be the same object is if the dipole is 0, and this is just, you've just flipped it upside down. And so if parity is a good symmetry of nature, d equals 0. Experimentally, we know this is not true because the W boson couples only to the left-handed guys and not to the right-handed ones. So if it was a symmetry of nature, everything would be hunky-dory. In practice, it turns out to be very badly broken, in fact, maximally broken. The other solution is CP, or equivalently time translation, because everything is CPT invariant. Well, not times translation, but time inversion. And so this is as it sounds. Time goes to minus time. And so again, how does the dipole transform? Well, that's just a function of position. So under a CP or T, the dipole goes to the dipole. But the spin is r cross p, and p has dt in it. And so the spin goes to minus spin. And so again, by the same argument here, it takes this neutron into that one, and the only way they're both equal is if the dipole is 0. So this is CP is also not a good symmetry of nature. In fact, it's also, roughly speaking, maximally broken. In the CKM matrix, the angle that breaks CP is pi over 3, roughly. And so that's very order 1, and it's a pretty large breaking of CP. And so we know that both CP and parity are not good symmetries of nature. And so what's going on? At the classical level, these are basically the two solutions you have available, and neither one of them works. OK.
I have a possibly very silly question, but to me, looking at that DUD arrangement, that looks like highly natural. If you have two negative charges and a positive charge, the two negative charges
yes, that's correct.
The opposite with the positive charge in the middle.
Mm-hmm.
It doesn't seem like that's something that, given the nature of electromagnetic interactions, that doesn't seem like something that necessarily needs further explanation to me. Why is that?
So the reason is that, so let's say we take the analogous thing, which is, let's say, a molecule of water. Right? So water is also made up of 3 things. It has some structure. And the question is, why is it the structure it is? And the statement is, the reason why it can relax to its equilibrium configuration which is roughly speaking, I guess for that, a tetrahedron, is because it has, there's an additional degree of freedom, which is what is this angle here? It can relax. This may be the, you would think is the minimum energy and is very good. But it requires you to be able to transition from this to that, right? And to formulate the question at all, you have to say you can transition from here to there. And the answer is we've measured the neutron, and there's only one neutron. And so the statement is there's nothing directly analogous to the rotational degree of freedom needed. This is actually links very closely to what the axion tries to do. And so the axion is a way to take this idea, which is to say, this looks very natural. And so what if we made this theta an actual degree of freedom? And then would it be able to relax into something like this? And the axion is actually a realization of that approach. And so what you described is basically the idea that leads pretty directly to the axion. Yeah. All right. So, but at the classical level, the statement is we just have observed experimentally that the neutron does not have this classical degree of freedom, the equivalent one. Yeah. All right. OK, so that took about 15 minutes. And hopefully in the remaining hour, I can tell you the exact same story, but quantum mechanically. So unfortunately, quantum mechanics to describe this problem is a lot more complicated and annoying. So let's go through that. I'm going to do it in a manner that's semi-historical. In particular, I'll sort of go through and describe what people expected, what they ended up seeing, and then how they sort of resolved all these problems. So the starting point is, well, we need QCD, right? We're talking about the neutron EDM. So we start with the Lagrangian for QCD. So the Lagrangian is going to be, you have what, minus 1/4 g squared, 1 over g QCD squared, plus I q d slash q. So right, you have your quarks and anti-quarks. So I'm actually going to be most of the time working with Weil fermions. Unless I have to do a Feynman diagram, then I'll do it in direct fermions. Just because almost everything is better in Weil fermions, except for doing a computation. OK, so and then you have Q, mu, md, Q conjugate, where my quarks, I've basically collected my two flavors of quarks for now. You can do everything I'm about to say with 3 flavors or more flavors, but for now I'm just collecting my quarks into a doublet of flavor here. And so the way under that your quarks and everything transform is that, so this is your base starting Lagrangian. You'll notice that partially because I wrote it with an up quark, down quark here, that we have some flavor symmetries here. So in particular, you have an SU2 left times an SU2 right times a U1 baryon times a U1A. So here, your quarks, Q and Q conjugate, transform as so I'm using sort of standard Dinkin diagram type notation here, which is just that these guys are doublet under one SU2, these guys are doublet under another. That's good for these 3 terms. The mass term is not, you'll notice, does not obey this. And so let's call this guy M. And so we're going to give it a transformation property that's this. So it's a spurion. You can sort of pretend it transforms under the symmetry. OK. And I guess let's put if you want. OK, so this is your starting Lagrangian. Experimentally, we have essentially determined that the way this guy behaves at, well, you can do a one-loop diagram, show that this guy becomes strongly coupled in the IR. And what happens is that QCD confines. And so the way, and in particular, it breaks chiral symmetry, which is the statement that we have measured that Q conjugate is not equal to 0. So in particular, if you take this experimental fact, what this means is that if you multiply these two guys together, you'll notice that they do not transform. They are not invariant under SU2 left or SU2 right or U1A. And so what it actually does is that this guy will break your symmetries down to, it actually breaks, so at this point, you'd say it breaks one of the two SU2s down to the vector, and it breaks U1A. And so the way people do this is they usually call this some field U. There's some, let's put proportional to, and then some f pi cubed to be the right dimensions. This U here is going to be your the way you parameterize your Goldstone bosons, right? Because every time you spontaneously break a symmetry, you get Goldstone bosons. It's a Goldson's theorem. And the typical way of writing it is U equals e to the I pi a over f. Let's call them tau a's. F pi. OK. And so how does U transform? You can sort of read it off from here, that U transforms under left bar 0, 2. That's a minus sign. OK. And so you'll notice that U breaks U1A entirely. So there's one Goldstone there. It breaks these two guys down to the diagonal. So you'll notice that if you set U, L, and R to be equal to each other, right? So under left and right, U goes to L, U, R dagger. I think that's the notation I'm using. Yeah. And so you can see that if you set, these are both unitary transformations. If you set L equals to R, these guys doesn't change. So you'll notice to leading order, this is the identity matrix plus dot, dot, dot. So if you set these two equal, they, it's still a good symmetry. And so that means we've only broken we've broken the axial combination of these SU2 guys. And so what we have is 4 pseudo Goldstones. So let's just write down the, we are all effective field theorists, so we just write down the most general Lagrangian consistent with the symmetries. We have U, we have this spurion M. And so we're going to Taylor series in our spurion M. So M is going to be small. Yeah?
Sorry, probably I missed out. When you, did you explain why did we take this particular age group?
So we're trying to mimic QCD here. So QCD at low energies is roughly speaking just the up quark and the down quark. And so you can include the strange quark as well. But just to sort of mock up the problem to try to approach this, this is a toy example of a theory that has something like the neutron. And we're going to try to calculate the neutron EDM in this framework.
And how can the QCD H group SU3C work up this way?
So the way things are charged under SU3, let's put it over here, SU3 color, is these are fundamentals, these are anti-fundamentals. And so everything M and U are both singlets under SU3 color. And so when we write down our effective theory, nothing is charged under SU3 color. And so sort of color drops out of everything. Yeah. Any other questions? All right. OK, so let's write down the most general Lagrangian consistent with symmetries. Let's see, in my notation, I did it like this. F pi squared trace of d mu u dagger, right? U is a 2 by 2 matrix, so that's why I put trace. So this is, I wrote this normalization such that it gives a normalized kinetic term. So if you take this thing, plug it in here, you get a standard kinetic term and a bunch of other additional higher order terms, but the kinetic term is correct. And then we're doing a Taylor series in M, so let's put it in M to first order. So first order, you get plus some constant I'm going to call A. You're going to again have F cubed for dimensions, trace of M, U, then you have plus the Hermitian conjugate. Okay. This is the most general Lagrangian consistent with symmetries, including the Spurionic symmetries here. So what you can do now is, you notice since M is a spurion, right, it's just a number. This actually ends up giving mass to our pseudo-Goldstones because our Goldstones were never really Goldstones to begin with. The symmetry I wrote down had something fake transforming under it. And so if you work this out, what you get is that you get two charged pion, or you get a complex degree of freedom, which is the charged pion, whose mass is, I think, A F pi mu plus md. And then you'd get two other pions, m1 equals A F pi times 2 mu, m2 squared equals A F pi 2 md. Okay. And so this would be your prediction for the pion spectrum. Now, people have gone ahead and measured and looked for pions, and what they have found is they've found this guy, but they have also have not found two additional light bosons. They have only found one, and that one is m pi, has a mass that's also basically the same as the also mu plus md.
I'm sorry, did I miss where you defined A?
It's just some proportionality constant.
Okay.
Since I'm just writing down, doing an effective field theory, I don't know what the absolute magnitudes of stuff are. And so it's just some constant that I'm going to set by matching with data. Okay. So this is a bit weird, right? We had thought we should have two, and instead we have one. And so how to proceed can sort of be seen by writing down this match matrix, which I did not write down in detail, in a little bit more detail. So if you take this guy, expand out the mass, and keep only these two terms, what you get is, let's see, you get a mass matrix that's A F pi over 2, some pi naught, some other particle called eta prime, mu plus md, and okay, let's squeeze it in here, pi 0 eta prime. So if you diagonalize this matrix, you'll get the two masses I mentioned before. So what you'll notice is that if, for some reason or another, your eta prime, which corresponds to the Goldstone of U1 here, and your pi 0, which corresponds to the T3, the 1 minus 1 of your vector-like symmetry, if one of them was not actually a Goldstone boson, then you would have only one boson, and it would have the exact same mass, or exact correct mass to match with nature. And that's actually the case. So actually, how many people have heard about anomalies before? OK, so I'm not going to go in detail about that at all. So the statement of the anomaly is essentially that U1A here is a bad symmetry. Even if you set the quark masses to 0, U1A is a bad symmetry. And it turns out, as you guys, I guess, have all seemed to have covered in your QFT class, that if you make the field transformation, I do not want to. Does this work? Whatever. I'm going to start erasing stuff then. Goodbye, classical. So if you make the field transformation, Q goes to Q e to the I alpha. And then I guess I also wrote Q conjugate goes to Q conjugate e to the I alpha. This is not actually a symmetry of their theory. What happens is it generates a term in your Lagrangian that's proportional to gluon tilde. And so this is essentially how this logic here with the pion masses is essentially how people then stumbled upon anomalies. So now, let's see here. Whoops. So since we all know about anomalies, let's apply our knowledge of anomalies to the chiral Lagrangian here. The statement is, in addition to this Lagrangian that I wrote up top, there's also an additional term that I did not write down, which is plus, I put g squared there, so it's theta gg tilde over 32 pi squared. And what we know is that, let's see, we can now take theta here and turn theta into a spurion. Just like how we took the mass term and made that a spurion, we're going to take the mass term, or the theta angle here, and make this guy a spurion. So in particular, the spurionic symmetry we're going to use is if we take Q goes to Q e to the I alpha, then theta goes to theta minus 2 alpha. This is a symmetry of the theory. OK, so what is this going to teach us? The first is that because U1A is not a good symmetry of the theory, what we have to do is over here, we're going to have to, here we go. So in addition to this mass term, we're going to have to write down a term that gives a mass to the eta prime, right? That represents the breaking of this anomaly being actually a bad symmetry. You might wonder, OK, so how do we do this? Well, in here, the eta prime appears as basically e to the I eta prime over f pi, or let's call it f eta prime, 1, 1, and I think I did 1 over square root of 2, right? Because it's 1, 1 here because you can tell based on how the quarks transform. And it's the identity matrix. And so what this means is that if you take the log of the determinant, I think it was, of u, this gives a term which depends only on eta prime. So when you take the log of the determinant there, it's some messy thing. Well, actually, we don't even need to take the log. If you take the determinant, right, you can see that you just get e to the I square root of 2 eta prime over f pi. So let's not even take the log of that. So what you do is say that, well, let's just write an additional term in this Lagrangian that's proportional to the determinant of u, which represents the fact that U1A is a bad symmetry. So let's write down a term B f pi to the fourth determinant of u. Now, B is going to be some arbitrary number, right? We're doing effective field theory here, so it's going to be complex. And in particular, its phase is going to be fixed by this spurious symmetry, right? Because we know that this is essentially this symmetry, and when you express it in this language here, right, is what? Eta prime goes to eta prime plus, let's see, there's probably some annoying square root of 2, f pi, let's see, there's an alpha, and I think there's a square root of 2 in the numerator. Yeah, okay. Well, let's call this f eta prime since it's not really part of the pions. So this means this guy here has a phase that's basically e to the I theta. And now B is a real number. And so we're going to take this plus its Hermitian conjugate. And we see that this means you have a term in your Lagrangian, which is, let's see, where is it? 1/2. Let's just put the mass of the eta prime squared times eta prime plus theta over square root of 2 f eta prime squared. OK, so if I did my algebra correctly, which it looks like I did, yes, this mass term has the symmetry that we wrote that it had to have. And yeah.
I'm sorry, I'm just a bit confused with your notation. So you wrote 3 different thetas?
There should be just one theta.
There's a theta there, there's a theta.
Yes, these are the same thetas. These are all the same thetas.
These are all the same theta?
Yes.
I thought that was a coupling.
Yeah, so there's this. The first thing you do is you say, in my UV theory, I have a theta, which is this guy. And because of the anomaly, the proper symmetry of the theory is this. Of the UV theory is this guy. Go through Peskin and Schroeder or some other thing. You'll find this is the correct symmetry. And then you say, OK, so that means over here, when I write down my EFT, I have 2 spurions to write it out of. I have M and I have theta. And so now I say, OK, now let's first say, how does U transform under this U1A, right? And since U equals QQ bar here, I can say this means I can work out how that means this guy transforms as e to the I think I just did alpha, yeah, alpha Q conjugate. And let's put the identity matrix here just because. And so you'll notice that this is equal to U. And in particular, there's a small part of U, which is e to the I eta prime times the identity over f eta prime. And I always did this over square root of 2. And so if you say then, if U goes to U times e to the I alpha times the identity, and you look at the eta prime, this looks like it just says eta prime goes to eta prime plus alpha. And so this means that this is the symmetry you had in the UV, but the symmetry you have in the IR is this guy. OK. So then you say, OK, so now I have the symmetry in the IR. I have my 2 spurions in my field. So what are the terms I can write down that are invariant under this symmetry? One is you first say that because we know that U1A is not a good symmetry, right? It's broken by QCD effects, that we have to write down a term that's basically some number, let's forget about it, what it is, times the determinant of U. Right? The determinant of U picks out only eta prime and doesn't pick out the rest of the pions. So if I wrote down this term, it gives mass only to the eta prime, which is what we want to do, because we've discovered that eta prime is not actually a Goldstone. And then we say, well, we have this symmetry here, eta prime and theta. And so that means the determinant of u is proportional to e to the I eta prime over f pi, or f eta prime, square root of 2. And so that means if I want this to, notice now I can pull this e to the I. So that means if I want this to be a good symmetry, which I know it is because of the UV theory I'm considering, that the phase of this guy, this coupling here, is actually completely determined to be this theta angle, just by the symmetries of the problem. And then I say, OK, now we've determined that EFD tells us that we know the phase of this coupling. It's not just some random coupling. We don't know its magnitude. And then we write down, now we can just Taylor expand in eta prime and get a mass for the eta prime. Yeah, so that's the logic. I guess I went through it a little too quickly, sorry. But yeah, that's the basic logic. You have to sort of jump between you use the UV to figure out what are all your symmetries, including, so here it's for theta. Then you figure out how those symmetries appear in the IR. And then you just write down all terms consistent with the symmetries. And just say, I'm an effective field theorist, write down everything. Yeah. OK. All right, so we now have our Lagrangian that we're considering, which is just these two terms plus this guy here. OK, so this is all nice and good. Eta prime, m squared eta prime, so just some numbers so that people know, roughly speaking. This is around, what, 900 something. Oh, did I not write these numbers down? That's embarrassing. OK, off the top of my head, do I remember? I think this is around 960 MeV. And the pions are about 140 MeV. And actually, a fun exercise, if people haven't done it before, is so we've actually measured the pi plus and pi minus to have a slightly different mass from the pion, pi 0. And that mass difference can actually be calculated by doing your standard quadratic divergence argument and cutting it off by the rho meson. And so if you, since people a lot of times will talk about naturalness, and this is an example of it, that's probably something that would be fun for people to work out. Yeah?
I'm sorry, I'm staring at this for I'm not quite sure. How did your eta prime and theta get out of the exponentials when you cross that arrow?
I Taylor seriesed.
OK.
Yeah. So both this transition, because I'm only interested in the mass term, which is the second order term, I Taylor series this guy. And to get the mass term, I Taylor series to this guy. Yeah, that mass matrix comes from Taylor expanding that.
Why can't B be complex and just not transform?
So the statement is, we know that there exists this symmetry, right? And so if B was complex and did not transform, then this term is not invariant under your anomalous symmetry here, right? It's sort of like if you had no mass term, you couldn't write down this guy if you just wrote trace of u. And so it's the same thing here. It's if you if this phase was not exactly theta, then this transformation, this term, mass term, would not be invariant under your symmetry here. And luckily, this is just some phase, and so you could just plop and say it's actually a very simple thing. It's just a complex number. If it was some matrix or other things, then you start having to worry about all these other things. Yeah. OK. All right, so that's almost it for the pions. Let's do another exercise, which is that now that we have this theory down, we can actually calculate you can actually prove that I lied slightly when I said this is proportional to the identity. In fact, you can prove exactly what it is. Well, it is true that it's proportional to the identity if you Taylor expand around pi equals 0. But the pions, in particular the pi 0, could obtain an expectation value. And in fact, it does when theta is non-zero. And so let's go through that really quickly, since it'll actually it'll connect back to the classical point of just is this angle equals 0 really a minimum energy configuration or not? So what you can do is say that now let's let pi 0, the pi naught have an expectation value. In particular, we let u equals e to the I pi 0, 1, 1, 1 minus 1 over square root of 2, f pi. And I'm just going to call this e to the I phi, e to the minus I phi. So let's expand around a point where, and phi here is just the expectation value of pi 0 over f pi and the square root of 2, but details. OK. So let's calculate, is phi equal this phi equals 0 a minimum of the energy, or does pi 0 obtain an expectation value? And so to do that, we expand this term, or just look at that term. Right? It's OK. Let's write down what is the mass term in slightly more detail. In fact, let's go all out when you calculate this. F pi cubed, trace mu e to the I theta mu md e to the I theta md times this guy e to the I phi e to the minus I phi. And I forgot to mention, so you'll notice here that eta prime obtains an expectation value that's minus theta over square root of 2 f eta prime, right? And this term here also has a term that's plus I, that's annoying. Also has a term, let's just write it here, that's e to the I eta prime over f eta prime square root of 2, 1, 1. So you can just take this thing, plug it in here, and it's e to the I phi plus theta e to the I theta minus phi. OK. Let's see, let's modify this then. This is theta minus phi. This is plus phi, theta minus phi here. And then plus its Hermitian conjugate. OK.
What does subscript some theta mean?
It's just the phase for the mass, because the mass can be complex.
OK.
So here, these are the absolute magnitudes. And I'm separating out the phases.
So that's a different theta from all the other theta?
Yes,
Okay.
that's right. In the end, you'll discover that only one theta ever matters. And so we'll get to that. OK, so now you don't need to do any Taylor expansions. You can just calculate what this potential looks like. Let's see. I'm not going to be able to remember this. This is equal to minus 2a f pi cubed times mu cosine phi minus theta bar over 2 plus md cosine phi plus 1/2. OK. You'll find it depends, it simplifies to this where theta bar equals theta plus theta mu plus theta md. All right. Okay, that's all nice and good. I think that's right. Okay. So now what you do is you just go to Mathematica and ask it to find what is the value of phi. It's some ugly number that's essentially tan phi equals mu minus d over mu plus md tan theta bar over 2. It's just some random number. You plug it in. And then what the final result, which will be useful, is when you plug in what's the value of phi into here. And you get what's the actual dependence of the vacuum energy on this value theta bar. And let's see. It is minus m pi squared f pi squared square root 1 plus 4 d mu plus md squared, and it's sine squared theta bar over 2. Okay, so
sorry, can you repeat what you're phi? Do you do?
You take the first derivative, set it to 0. You literally just minimize it. Yeah. Since this is just the expectation value of a field, you want to set it equal to its local minimum.
Yeah.
Or to the global minimum.
And is that a tangent of theta bar over 2?
Yes, that's right. Tangent theta bar over 2. Okay. So what you'll note is, first things first, this has a minimum at theta bar equals 0. You will see that actually has some amount of that this theta bar angle has some amount of correlation to what the classical picture called theta, which was the angle between the up and the down quarks. Of course, you can never make a comparison like that particularly precise because classical physics is a very bad description of quantum mechanics. So yeah, but it's sort of intuitively, you can sort of say in spirit that's sort of what's happening. Let's see. All right. Okay, so now let's finally, now that we have all this set down, okay, first things first. So why did this theta bar appear, right? Why is it that I had all these angles that are all crazy and annoying to keep track of, but it all simplifies to a single angle? So the reason is that you can use symmetries here to set various quantities to 0, right? So I have one term in this Lagrangian here, let's say this mass term, let's write this in a little more detail. It's mu u conjugate, right? And let's say e to the I theta mu. You'll notice that by doing a field redefinition, u goes to u times e to the minus I theta. Here, I can make this a real number. And when I do that, what happens is that exact field redefinition is anomalous, and it sends theta into your theta angle, which is this guy here. So when I use a rotation to set this guy to be real, it turns out that this theta angle appears here now as now theta plus theta mu. You can do the exact same thing for the down quark, which is theta plus md. And so you can see that I could have done everything just by using field redefinitions to rotate all angles into a single angle at the very beginning. But it's sort of amusing and it's sort of instructive to make sure you got everything correct, to keep all the theta angles completely separate and then just at the end discover that your physical quantities only depend on this combination, right? Because any single one by itself is unphysical because I could set it to 0 by a field redefinition. OK. All right, so now let's finally, wow, that took a really long time. OK, let's finally get to the neutron EDM. OK, so to do this, I wonder if I should have erased this. This was probably a bad move. Oh well, I'm committed. What you have to do is now put in the neutron into your theory, right? Because right now, I just wrote down theories, particles that we knew had to exist, right? The pions. Now, experimentally, we know that the neutrons exist. So let's put them in based off of symmetry properties that we know of the neutron. So the neutron is equal to, right, is U up quark, down quark, down quark. There's also a neutron, a right-handed neutron, which is just up conjugate, down conjugate, down conjugate. And so if you then ask, well, how do these objects transform under the spurions, or the symmetries we had, right? SU2 left times SU2 right. If you work out carefully through the spinor structure here, you'll discover that this guy transforms as left, and this guy transforms, I think that was the notation, or the bars go in the right way there. So that, actually that looks a lot like an eta. Let's turn that into capital N's. OK. So you see that the left-handed neutron just behaves just like a left-handed field. The right-handed neutron changes just like a right-handed field. These are actually, well, really what I did here is actually, this is what I really wrote is q cubed, and here is q conjugate cubed. So n is equal to your neutron proton when you work out the indices. OK. OK, so now we have written down how our neutrons appear in our Lagrangian, or, well, what are their symmetry properties. So let's now write down how they actually transform. Write down, again, the most general Lagrangian, coupling neutrons to pions to everything. So the reason why you need to couple neutrons to pions is you'll notice you cannot write a mass term here. Right? If you write mn, n, and conjugate, this is not, you can't write this mass term because the left-handed guy is left-handed, the right-handed guy is right-handed, and so you need something to bridge the two. And so that's the pion field, which is charged. Again, I should have worked through this better. Oh well. So I have to take the complex conjugate, stick it in there, and I can have a mass term. So there's 3 other terms that you can write down that will be of interest to us. The first is minus C1 and times the mass matrix and conjugate, right? This is just the statement that the masses of the quarks means that the proton and neutrons have different masses, so you should write that down. There's another term, C2, and U dagger, M dagger, U dagger, and conjugate. This is just the same term here, but with some some pions thrown in. Notice you'll need to throw them in because I wrote down M dagger here rather than M. And finally, the last term is I over 2 plus n conjugate dagger U dagger, I think, yeah. U n conjugate. Okay. So for various other reasons, this other coupling is GA, they call it GA minus 2. It's just some number for now, right? We have some 3 numbers here. And so again, as before, we have to fix all these guys by experiment. It turns out we don't need to figure out what C1 or C2 is separately. It turns out that only the sum of the two matters. In particular, if you Taylor expand this guy to first order in the pions, well, first things first, if you just set the U equals to the identity matrix, you'll see that the C1 plus C2 determines the proton-neutron mass difference. And so what we actually know is that C1 plus C2, let's just call this C, is something like 1.7, I think it was. So actually, I lied slightly. The proton-neutron mass difference is not the best way to get this because there's an electromagnetic component. And so what people do is they just write the 3-quark version of this. And then there's a difference of neutral pion mass, or neutral proton-neutron baryon masses that will give you this value. But that's sort of a minor detail. We use the masses of the various baryons to give you that. There are several ways to give you this guy here. The way that's sort of easy to understand but doesn't give the best value is just say this mediates, well, I guess I should write down, expand this in terms of pions, right? Because of the derivative, you can't set U equals to the identity matrix there. Okay, so if you take this term, write it out in terms of to leading order in pions, it looks like minus I G GAMN over F pion, your pions, and ratio 2 and conjugate. So what it is leading order is just some coupling between the pions and the neutrons. And what you could do is, for example, this couples the proton to the neutron via a charged pion. And so you could just do proton-neutron scattering. And the 0th order, the leading contribution will be a single pion exchange. And you can use that to determine GA. The way they actually do it is that if you turn these derivatives all into covariant derivatives, you can include the W boson, right? Because the W boson is charged entirely under the left-handed. And so you can calculate the decay of the neutron via the W boson. And GA not equal to 1 is actually a slight departure from being purely left-handed couplings to the neutrons. And we've measured it to be what, 1.3 or was it? Yeah. GA 1.3 roughly. And so now we have two interactions. This guy here, notice that this is a CP conserving interaction. And then you have C1 and C2, which are CP violating interactions, which are essentially theta bar C reduced mass over F pi A and tau A and conjugate plus, well, I guess minus this. Yeah. Okay, so your Lagrangian is this. So if you're familiar with Dirac notation, whether or not this has an I is imaginary or it's real is a difference in gamma 5. So in Weil notation, which is what I'm doing for now, the difference between having a gamma 5, so being CP preserving or CP violating, is whether or not the coefficient is imaginary or real. Just a minor detail in case you were wondering why I said this was CP violating and this CP preserving. I guess I didn't define mu. Mu is just the reduced mass, mu, md, mu plus md. Okay. So at this point, we can now just do a Feynman diagram and calculate what is the proton or the neutron EDM. Let's grab 2. Okay. So what you do is you just say you have a neutron. It converts into a proton via a charged pion, radiates a photon, pi plus, good neutron. So this is interaction which will generate a neutron EDM.
Shouldn't it be pi minus because you've got a neutron and then 2 pi?
Yeah, sure. I guess the proton p bar, whatever it is, yeah. If this is a proton versus antiproton, yeah, it's that. But okay, so you draw some your diagram here, and you're going to now just do your calculation. Let's see, I have 10 minutes. That's not enough to actually do the calculation, probably. So the basic way you do it is you say a neutron EDM looks like, in Lagrangian formulation, is I times some dipole f mu nu n bar gamma. I guess I'm doing Dirac, so sigma mu nu. Well, yeah, I'm doing Feynman diagrams, so I guess let's go to gamma mu nu, gamma 5 n. So this is the dipole operator in Dirac coordinates, I guess, or Dirac fermions. And so what you do is you say this generates some diagram, right? That's just a matrix element. That's some silly thing. It's what? There's a 2d q nu epsilon mu u dagger gamma mu gamma 5 u. And so what you do is you take this guy, which is going to be some horrendous integral that you just sort of pound through. The various tricks you use is, first you say that what I'm measuring here when I do the experiment is the dipole moment is basically at low energies. So I take the limit where the energy of the photon goes to 0, so that I can neglect higher order terms that are not linear in Q. Take this thing, mash it a bunch. You can do it for homework if you want. I don't know. Or just plug it in to look it up. Up to you what you find. Yeah. That's just some antisymmetric gamma mu minus gamma mu, probably over 2. It's the antisymmetric combination of Pauli matrices, or, well, yeah, Dirac here. Okay, so it's not particularly rewarding, but you go through, take this diagram, pound it into a form like this, and then you say this coefficient out here is your dipole moment. And what you get is, let's see, do I have any space anywhere? Oh, what you get is that your dipole moment is just charge times theta angle GA C 8 pi squared f pi squared, this reduced mass, and you get a log lambda squared over m pi squared. This is of order 4 because lambda is your UV cutoff, so that's 4 pi f pi roughly. I guess you can see what your UV cutoff is by, I guess I erased it, but if you write down, look at the kinetic term of your theory, you can see that it breaks down. It has a lot of high dimensional operators, and it breaks down at a UV cutoff of about 4 pi f pi. And you go through, plug in a bunch of numbers. This is about 3 times 10 to the minus 16 charge centimeters times theta bar. You compare that to what we had before, which was, 10 to the minus 26. So you see that theta bar is 26 charge centimeters. So theta bar is less than 10 to the minus 10. Okay. So this is essentially how you get the strong CP problem in quantum field theory. I took a very bottoms-up point of view. Let's see. So I have only 5 minutes, so I'm probably not going to really say anything else. So just a quick show of hands. Who was more interested in theory aspects of basically what is the meaning of theta bar versus who just wants to jump into models and various solutions of these things? So maybe like who would prefer instantons? And who would prefer just sort of model building solutions? Okay, so instantons seem to be a fairly clear winner here. Okay, so next time I'll go over instantons and just what is the meaning of theta bar here. To give you a hint of basically why it's non-trivial, let's just erase over here. So why there's a huge part of the story that I've not bothered to tell people yet. This is essentially due to 2 confusing facts. So you have this term in the Lagrangian, which is theta over 32 pi squared g tilde. The first confusing fact is I added this to my Lagrangian. And so let's just have a Lagrangian that's just this plus g squared, right? The simple thing of just QCD, like Yang-Mills. If I write down what is the Hamiltonian of this theory, the Hamiltonian is just basically e squared plus b squared, but with color. There is There is absolutely zero dependence of the Hamiltonian on theta. So this is kind of striking and should confuse you, right? Because how do I go from state 1 to state 2? I apply the Hamiltonian. So how is it that theta has some physical effect, right? If it's in the Lagrangian and I'm just using my Hamiltonian to evolve, this is shouldn't have an effect. A related thing is if you look at theta GG tilde, okay, I have to go super fast. Let's see. This guy here is a total derivative. GG tilde equals d mu of this absolute ungodly mess of indices on d a mu a times f rho sigma a minus g over 3 f a b c rho sigma. So it's a total derivative, and everyone's always taught that total derivatives have no effect on nature. And so you'll notice that theta, when I took a pure EFT point of view, has a huge effect, right? But I'm now giving you arguments that it shouldn't have any effect at all, right? It's a total derivative. I think it was Stokes or someone like that, some integral person told you that the volume integral of this guy should be the area integral of this guy at infinity. The current at infinity is 0, so this whole surface integral or volume integral should vanish, right? The Lagrangian has d4x. This should be equal to 0 because integral d4x equals integral d cubed x of this current at r equals infinity. And if you want finite energy and things like that, everything vanishes at infinity. So what the hell is going on? And I guess I'm a little over time, so I'll just leave it at that. And yeah.